Last time we learned about an algorithm called depth-first search, or DFS, which is a fundamental graph traversal algorithm. And even to this day, I guess it is my favorite graph traversal algorithm. Part of that is because of its really elegant recursive presentation. Another reason, though, is I guess it has a special place in my heart because it was the first graph traversal algorithm that I learned about, and that really changed a lot in terms of how I thought about the study of algorithms. But there is another fundamental graph traversal algorithm, and I've already made quite a big deal in this course, maybe it's sort of an obsession of mine, about a certain sense of duality, about how cases where we have a pair of algorithms or a pair of data structures that are sort of dual to each other. They're sort of complementary to each other. They're two sides of the same coin. And I think that's definitely true of depth-first search and its complementary algorithm breadth-first search, or BFS. And so we'll spend a lecture now talking about BFS. And one of the reasons I wanted to cover BFS second was, again, because I like DFS. That's a valid reason, frankly. But also because I think when you first see BFS and you look at its results, it tends to be that the results of BFS are sort of aesthetically pleasing. They look very nice if we draw them onto a graph. And that might mean that if we saw BFS first and then presented DFS, people might be wondering, what's the whole point of DFS? It looks sort of ugly by comparison. And that's valid. I actually agree with that. It turns out that the trees that BFS produces do actually have a lot of aesthetically pleasing qualities, and there is a characteristic, sort of a signature aspect of BFS that can be really beneficial in some cases, and that also I think is responsible for the trees looking nice. And so I figured by presenting DFS first, that way we'd give it its, a fair shake. We'd be able to understand that it is actually accomplishing something pretty interesting, pretty profound. Although yes, it's true that frankly DFS trees look sort of ugly next to BFS trees. All right, so as we saw in the last lecture, DFS has this elegant and I think intuitive recursive implementation. We just keep wandering around the graph and visiting vertices, because if our goal is simply to traverse the graph, to explore every vertex that we can visit from some particular starting point, then I think it's quite intuitive to wander around the graph, and if you encounter a new vertex that you have not visited yet, go visit it. And that's this recursive presentation of DFS. But like any other recursive algorithm, because really recursion is sort of a proxy for using a stack, it's a clever way of structuring algorithms such that a stack is being used behind the scenes, that being the call stack. Because it's a recursive algorithm, we could implement DFS using a stack and write it iteratively. So we could look sort of like this. Now, there are a whole bunch of different ways I could write DFS iteratively because the exact structure that I use depends on which of the different combinations of visits I want to perform. So we saw in the recursive presentation, we could visit a vertex, fully process it, do whatever we're supposed to be doing with this traversal before we visit its neighbors, or we could visit the vertex and process it after all of its neighbors have already been visited. And depending on when I want to do that, I might rewrite this iterative DFS. But here's one example of iterative DFS. So I use a stack, we'll call it S. I begin by marking all vertices as unvisited. I then have some root vertex of my DFS tree, we'll call that R. And I push that onto my stack and I mark it as visited. And then I just keep iterating as long as the stack is non-empty. I take a look at the vertex on the top of the stack. And the logic I'm going to use here, let's draw the stack. So here's the stack. This is the top of the stack up here, obviously. Suppose my stack looks like this at some point in the algorithm. There's A, B, and C, and then there's X, and there's Y. Okay, the logic I'm going to use, and there are a bunch of different ways of implementing this, so this doesn't have to be the only way we implement DFS iteratively, as I've said. The logic I'm going to use is that I'm going to leave a vertex on the stack until all of its neighbors have been visited. And the idea there is that suppose I am at vertex Y and I choose to visit some neighbor Z. Okay, so I push Z onto the stack, and then you can see at the next iteration of the algorithm, I'm looking at the top of the stack. That's the way stacks work. So I process vertex Z. And maybe I process a bunch of other vertices as well. Eventually, though, we get back down to vertex Y, and I'll explain the logic of how that works in a minute. We get back down to vertex Y, and so I take a look. It's still on the stack. And then I ask, have all of its neighbors been visited or not? If we discover that all of the neighbors of the current top vertex have been visited, well then I guess we're done with that vertex and we can remove it from the stack once and for all. Otherwise, we leave it on the stack, so suppose there are still more unvisited neighbors of Y, and then we choose an unvisited neighbor, let's suppose it's called W, and push that on the stack. And the idea is that way, by leaving Y on the stack, that means that when I'm finally done at W and I come back down, I can then check whether Y still has any unvisited neighbors. Remember that if Y had unvisited neighbors at one step, by the time I get back there later, y's unvisited neighbors may have been visited by some other direction. So this is my vertex y, and it has, let's say, 3 unvisited neighbors, and one of them is the vertex w. Well, of course, in DFS, suppose we choose to go to w first, so there we go, and then w has been visited. Later, when we're done at w, we're going to backtrack to y, but it's possible that by then, let's say this neighbor has already been visited. Maybe it was visited indirectly somewhere further down the road from w. But I want to check anyway, because maybe this other neighbor that I clocked as being unvisited last time I saw y is still unvisited. So I leave y on the stack until all of its neighbors have been visited. Okay, so that's the basic idea behind how I'm going to use the stack. The algorithm itself is saying, well, the stack is non-empty. Well, there are still vertices left that may have unvisited neighbors that I've already encountered. Take a look at the top vertex. If all the neighbors have been visited, just delete it because we're now done with it. Otherwise, it must have at least one unvisited neighbor. We'll call that W. Mark W as having been visited and then put it on the stack. And we're going to notice in this lecture, with these iterative algorithms, we often mark something as visited as we add it to our data structure. The actual visit itself might happen a little bit later, just because of the mechanics of processing, because it might take a few operations. I might have to go back around the loop before I actually see vertex W. Maybe you can observe in this case that because I push W onto S and then immediately wrap back around in my loop, clearly the stack will be non-empty if I just push something onto it. It turns out that actually W will be processed pretty much immediately. Like as soon as I get to line 7, W will definitely be the top of the stack. Okay, so here's one implementation of iterative DFS. Now, it's a sign of how much I like DFS that I've allowed DFS to barge into the lecture that was supposed to be about breadth first search, or BFS. But don't worry, I'm going somewhere with this. Let's just run through a quick example of our iterative DFS algorithm, starting at vertex A in this graph. Because at the beginning of the algorithm, we just start at some starting point R, and we push that onto the stack, I'm going to assume that we've already done that. So I've pushed vertex A onto the stack, which means at the beginning of my iteration, at the first iteration of the while loop, the stack, of course, is non-empty, and then I'll mark A as visited. And then the next thing I do is I pull A out and I verify that it does have unvisited neighbors, and then I choose one of them to visit next. So in the pseudocode, it just says next unvisited neighbor of V. So we've left this vague as to how we choose the next unvisited neighbor. This is sort of like back when we talked about quick sort or quick select, where I just said choose a pivot, because I suppose that there are different ways I could do this. In this course, though, we have adopted the convention for DFS, and we're going to adopt a similar convention for BFS, that if there are multiple neighbors to choose from, so in this step, I could have chosen R, O, or B. If there are multiple choices, I always choose the one that is lexicographically lowest. So for cases where the vertices have letters, then I would choose the one that's alphabetically smallest, so I would have to choose B. That is a convention that we will apply universally unless I specifically state that an exception is being made. So that includes on assignments and exams and things. It is always assumed that when there is some ambiguity of which neighbor I visit next, if there are multiple candidates, I always choose the one with the lowest number or the one that comes alphabetically first. Okay, so in that case, because I did find an unvisited neighbor of A, I leave it on the stack and I push B on top of it. And so we can see at the next step, I'm going to be visiting B. There we go. I choose between its two unvisited neighbors, C and P, and of course C goes first. And then I'll start going faster here because I think we already know what DFS does. So then I go to D, and then E, and then F. And because of the way I've laid out the names of vertices, we actually end up wandering up this branch up here. And we can see that we're pretty much guaranteed to get stuck in a minute. So here we go. We reach vertex R. So recall my statement from earlier about how earlier we left vertex A on the stack, and of course vertices B and C and so on, because we thought when we finally unwind back to vertex A, or to vertex D or something, it may still have unvisited neighbors. At the time, A had two other unvisited neighbors. They were R and O. But notice how, just like in the recursive DFS, it's possible that somewhere down the road, those vertices get visited. So by the time we actually get back down to A, it's quite possible that there are no unvisited neighbors left. But we leave it in the stack just in case. Okay, so at this point we have to unwind because there is nothing left to visit from R. And we'll notice that we end up unwinding all the way back to F. The way that happens in the iterative algorithm is At this point, we pop R off of the stack, and then we go back, and the next iteration looks at I, and it checks that whether there are unvisited neighbors, and there aren't, so it pops I, then H, then G, and then finally with F, there is at least one unvisited neighbor, so we leave F on the stack, and then we can proceed down to J. So we unwind all the way back to F, but then we leave F on the stack, we don't go any further down, and then we push J onto the stack and proceed with the traversal. Okay, so there's J, we then go through K, L, and then M, and N, and O. We get stuck again. Notice that as of this point, A no longer has any unvisited neighbors. So when we finally get back down to A, we will just be able to pop it off the stack. Okay, so we have to unwind again. We unwind all the way back to M, which still has unvisited neighbors. There we go. And then we proceed up to Q and then P. And at this point, we just begin popping things off the stack. So at each iteration that follows, we just pop the vertex because as you can see, every single vertex has now been visited. All right, so when the stack is finally empty, that means that our traversal is complete. Now in this graph, which was connected, we visited every single vertex. But remember that it's completely valid for there to be other vertices that were never visited at all because they are not reachable from our starting point. And of course, in that case, when the stack is empty, the traversal is still complete, even if there remain some unvisited vertices. Now, depending on what you're performing the traversal to achieve, how you figure that out or whether you care about that or track that is sort of up to you. We saw last time, though, that if I were to use a parent array to keep track of the DFS tree, it would be very easy to keep track of which vertices had never been visited because they would never have been assigned a parent. So recall, a long time ago in this course, I mentioned that if ever we find ourselves designing an algorithm that uses a stack, we should ask a question, which is, what happens if we use a queue instead? And the reason I made that observation was because at the time I was sort of observing that I thought that queues and stacks were sort of dual to each other. They were two sides of the same coin, last in, first out order versus first in, first out order. And arguably that might be why the algorithm we're about to produce, which is called BFS, is the dual of DFS, because it's essentially the same algorithm, but instrumented with a queue instead of a stack. Okay, so the question here is, I've just designed a stack-based iterative algorithm, and is there a way that I could develop this with a queue instead? Now, there are going to have to be some changes because there are certain aspects, because really this algorithm is meant as a way of representing an iterative form of recursion. It's an iterative implementation of a recursive algorithm. And we know that recursion plays well with stacks, but not with queues. Queues don't really mix with recursion. So we'll have to make a few changes to make this algorithm to implement this algorithm with a queue, but I think we can get the same overall effect. Instead of using a stack, we create an empty queue. We push our starting vertex into the queue instead of the stack. We mark it as visited. Then we keep iterating as long as the queue is non-empty. And then we want to work with the neighbors, but we wouldn't do it exactly this way because unlike the stack, where we put a vertex on the stack and we push on one of its neighbors, later that gets popped from the stack and we end up back where we started before we return to any vertex before vertex Y. Okay, well that is a consequence of the way stacks work. It wouldn't really work that way with a queue. So we have to do a couple of adaptations inside the loop, but we can achieve pretty much the same effect. We can in fact perform a graph traversal using a queue instead of a stack. So basically, the problem with using a queue is that this unwinding logic doesn't make sense with a queue versus a stack, because the unwinding logic is a way of representing a characteristic of recursion. But if we translate the algorithm to use a queue, we end up with something like this. So I create a queue, I enqueue something into it, and then I mark it as visited. While the queue is non-empty, I do the following. So I dequeue the first thing that's in the queue. Okay, but now it's not in the queue anymore, which means that if I want to make sure all of its neighbors get visited, I better do that now. So I iterate over all of the neighbors of my vertex, and for any unvisited neighbor that I encounter, I mark it as visited right now, and then I add it to my queue. Notice that the actual visit probably happens around here. This is, of course, just a framework, so I haven't added any other meaningful work to it, but the actual visit happens on the iteration where I remove a vertex from the queue. So I mark W, the neighbor, as visited, and then I add it to the queue. In a sense, I'm putting it in line to actually be properly visited. So I mark it as visited so that nobody else adds it to the queue, because each vertex should only get in line once. So if I suppose that this is my vertex V, and then I've got various unvisited neighbors of the vertex, what I'm going to do is, let's call these ones A, B, and C. what I'm going to do is iterate over all of the unvisited neighbors, and if I think of my queue here, which has got, let's suppose it's got some other stuff in it already, X and Y, I'm going to iterate over all of my unvisited neighbors, A, B, and C, add them each to the queue, and when I do this, just like with the convention in DFS, where I always work in alphabetical order, when I add multiple neighbors to the queue, I will add them in alphabetical order, as you can see I've done here. So I'll add them to the queue to line them up for processing, but in so doing, I will mark them as visited because that means they're already in line for processing. They will be processed shortly. Nobody else should add them to the queue. So the key observation here is that I mark it as visited before the actual visit takes place, once it becomes inevitable. This is a bit weird, if that seems a bit convoluted. I understand. I actually considered whether I should call this something other than visited. I should say mark it as found or mark it as enqueued. And I decided after a while that that wasn't really going to help anything. That is, in any event, we'd have to have this long explanation of what exactly it was I was up to. And so it's easier just to keep using words we've already been using. So this traversal is called breadth-first search, and the reason for that will become apparent once we see what it does compared to depth-first search. And as I said, so I guess this is my opinion, I consider this to be a sort of dual counterpart of DFS. It is also a fundamental graph traversal. It also produces a traversal tree, but the traversal tree looks characteristically very different, and it has different attributes that could be advantageous in different situations. All right, we'll use the same graph as before, and we'll start at the same place, and we'll perform a BFS traversal. So now I have a queue instead of a stack, so I'll put the front of the queue on top. And now I represent a different state of a vertex, which is that unlike before, where either a vertex was visited or not, in this case, I have to represent the state where the vertex is in the queue, but has not fully been processed yet. So a vertex gets properly visited when I remove it from the queue. But when I add it to the queue, I mark it as being visited so that nobody else also adds it to the queue. One of the main reasons I do that is because I don't want vertices being added to the queue over and over again, because then the queue might end up being really large, like larger in size than the number of vertices, and that could become a running time problem among other things. So what I'll do is color vertices this sort of straw color, I guess sort of a yellowish color, if they're in the queue, which means nobody else is allowed to visit them, but they haven't actually themselves been visited yet. The visit itself happens when the vertex gets removed from the queue. Okay, so I begin by adding my starting vertex A to the queue, and then each iteration of my loop, as long as the queue is non-empty, I remove the first thing, and then I look at its neighbors, and I add any unvisited ones to the queue. Okay, so the first step is visit vertex A. So when I'm actually visiting a vertex, I will shade it green as before. And then I add all of its neighbors, all of its unvisited neighbors to the queue. I add them in alphabetical order. So just like before, if the vertices are lettered, if they have letters, then we use alphabetical order. If they have numbers, we use numerical order. So I add B, then O, then R. Okay, so that means that now A is fully visited. So at the next step, I will color it blue because we will never visit it again. It is now fully processed, it's been added to the queue, it's been removed from the queue, and its neighbors have been inspected. We will never see it again. Unlike the iterative DFS, where a vertex remains in the stack for a while to make sure all of its neighbors have been visited, once I process a vertex in BFS, at the end of that step, all of its unvisited neighbors are in the queue, and the vertex never needs to be processed again. So at the next step, I'm going to pull vertex B out of the queue. So there we go. And then I'm going to add its two unvisited neighbors, C and P, again in alphabetical order, behind whatever's already in there. We just skipped over a slide that pointed out that when I visit a vertex from a particular direction, so when I added B to the queue, it was from vertex A, so B was added as a neighbor of vertex A, then the corresponding edge, the edge AB or the edge AR or the edge AO, becomes part of the BFS tree. Now the pseudocode I showed a minute ago didn't talk about the BFS tree because, as we saw last time, whether we actually choose to save the tree is a question of what we're going to use it for. We may not need to save the edges of the tree. We'll see an example of how we would do that in a few minutes. So it's similar to DFS where we could use a parent array. But the edges along which we actually perform the visit, the edge between a vertex and one of its unvisited neighbors that's added to the queue, that becomes a tree edge of my BFS tree. All right, so I then proceed with vertex O, and I add its unvisited neighbor N. And what I will observe at this point, I think the slide is doing that too, yes, is that if we take a look at the BFS tree so far, notice that it seems to be creeping outwards from our starting point pretty evenly. Whereas if we think about what DFS would have done at this point, this number of vertices in, DFS would have just, raced off as far as it could away from the starting vertex in some cases, just in an arbitrary direction, frankly. Like the direction is determined sort of by the naming of the vertices. And DFS, being so adventurous, just wants to push into uncharted territory as fast as it possibly can. Whereas what we seem to be doing with BFS is spreading out in a relatively conservative way from our starting point. We're spreading out evenly and slowly from our starting point, and that turns out to be a pretty big deal. Okay, so from vertex O, we visit vertex N. It gets added to the queue. We pull out vertex R and then add vertex I. Notice that vertex R actually has two neighbors, neither of which have been fully processed. Both I and C, as of the time when we reach vertex R, both I and C have not yet been fully visited. But because C is in the queue, we don't touch it. That's why we marked C off as visited, because we don't want to add it to the queue again, because it's already nearing the front of the line. So we only add vertex I. And then the edge Ri becomes part of the BFS tree. Another reason why we shouldn't visit vertex C is that if we added this edge, we wouldn't have a tree. We then have a cycle, which we're not allowed to have. Okay, so we keep going, and notice that the queue sort of grows and shrinks. In certain cases, the queue expands by a lot. In certain cases, only expands by one. But we are making progress through traversing the entire graph here. Okay, so we now pull vertex. If you look at the end of the last step, the thing at the front of the line was vertex N. We pull that out of the queue, and we notice at this step, vertex N has no unvisited neighbors. So we don't do anything. We might perform whatever operation corresponds to visiting the vertex. We might process the vertex, but we add nothing to the queue. It's sort of a dead end, although it doesn't feel the same as the dead end in DFS, because all we know from vertex N is that we've just managed to get to vertex M. It's one neighbor that has not yet been processed. We've managed to get there via some other path faster, pretty much. Okay, and so then we visit vertex I, and we can see that we continue to fan out pretty evenly from our starting point. Okay, here we go. And after a while, we reach a point where every single vertex we pull out of the queue actually has no unvisited neighbors left to process. So at this point here, we've got K and J left in the queue, but we know that when we finally get to both K and J, they will not have any unvisited neighbors, and then nothing will happen. We'll just visit them and then throw them out, or do whatever processing we need to do, but not expand the tree any further. And eventually, there will be no vertices left in the queue at the beginning of an iteration, and in that case, the traversal is complete, just like DFS. And we can observe here that we have indeed visited every single vertex reachable from our starting point. And because the visits were conducted along edges, if there were some vertices that were not connected to A, that were not reachable from A, we would not have visited those. So we now have another fundamental graph traversal algorithm, another way of starting at some particular vertex and then visiting everything reachable from it, and as we go, building this BFS tree that describes a way to get, or exactly how we reached each vertex from our starting point. So we can also save the BFS tree using a parent array. And so this is a graph that we did a DFS traversal on last time. I want to do the same traversal, or traverse the same graph with BFS and produce the parent array so that we can talk about what happens with this BFS tree. And observe that the BFS tree does look quite a bit different than the DFS tree. I believe that the term I kept using for the DFS trees was that they were stringy. They seem to have a lot of these cases where in the DFS tree you had a bunch of nodes with only one child. And that seemed to mean that if I look at a path from the root down to some leaf of the tree, it tended to be very long and stringy. We'll observe that BFS trees don't look like that. And it'll be clear pretty quickly that that's happening. Recall, for example, that in the DFS tree we produced on this weird-looking graph, we ended up with something like this. If I wanted the path from A to Q, DFS gave me this path. And that seemed a bit excessive. Now, I said at the time, and I'll say it again, that it isn't really the case that a path with more edges on it is bad, but it seems intuitively as humans, if we had to choose a path, we would try to choose a path that was sort of direct, with as few edges as possible. And it is possible to get from A to Q in 2 steps. I just do this. But for some reason, just almost random chance, although it wasn't really random, it just felt like because DFS wanders around sort of aimlessly, it took quite a while to find Q, and by the time it did, we had done so along a path that was really bizarre. So let's watch and see what BFS does for the same path, for the path from A to Q. Okay, so we put A in our queue, and then we remove from the queue, and we add all of its unvisited neighbors. Now, at the beginning of our traversal, A will become the root of the BFS tree. So what I'll do is mark it as the root by simply saying it has no parent. That is the unique property that the root has. I then add every unvisited neighbor. And when I do that, observe that I actually want to set the parent of each of its neighbors when I add them to the queue. Because I view that, I guess I view it like I am adding B to the queue from A, and I'm adding D from A. And so if ever there were a good time to set the parent of a vertex, it's when it is added from that parent vertex. So here what I do is I set the parent of a vertex as I add it to the queue, not as I remove it, because it's much harder to figure out what the parent was after you remove the vertex from the queue. Okay, so in this case, we already have our BFS tree is already forming to say there's A, and then its immediate children in the tree are B, D, now that's B again, there's D, and then we've got R and T. All right, and so then we proceed through. The queue is not visible in these slides, but hopefully if you need it, you can draw it out separately. Generally, if I were performing a BFS traversal on paper or something, I would keep track of what's in the queue, but the slide is already crowded enough as it is. Okay, so as we get to vertex B, we then add its unvisited neighbors, and so that means that C, E, F, and G become children of B in the BFS tree. Notice that this is an undirected traversal. When we did undirected DFS, we occasionally exposed back edges, and we never exposed any cross edges. In none of the examples in the last lecture where we did an undirected DFS did we see cross edges. And it turns out that that's because in an undirected DFS, cross edges are impossible. You will never see a cross edge in an undirected DFS traversal, whereas in an undirected BFS, cross edges can show up all the time. So notice how if we understand that B is the parent of both of all of E, F, and G in the BFS tree, well, that means this edge here is bridging between two separate branches of the tree. It doesn't go between a vertex and its ancestor. It goes between two siblings in this case, two vertices on different branches of the tree. So it is a cross edge. So unlike DFS, BFS may expose cross edges on an undirected graph. Now, as I mentioned a minute ago, it actually turns out that DFS will never do that. Not just that we didn't see it last time, but that it's impossible. So an interesting exercise to do, and one that gets spoiled a little bit by a proof that we write at the end of this lecture, is to prove that a DFS tree on an undirected graph will never have any cross edges. And the way you would do that pretty much is to assume that a cross edge exists. So suppose that we have a situation like this in our DFS tree, and this thing is a cross edge, and prove that if that happens, that DFS wasn't properly performed. That is, if we run a proper DFS, then this would have to be a tree edge, because we visit one of these branches first, and I don't want to spoil any more than that. Another thing we could prove is that in a BFS tree on an undirected graph, we will never have back edges or forward edges. Now, we're used to the idea that on undirected graphs, traversal trees don't have forward edges. We saw last time that really there's only one type of edge that goes between ancestors and descendants in a undirected traversal tree, and we've chosen to call that thing a back edge. But it turns out that is impossible in a BFS tree. There will never be back edges or forward edges if you perform BFS on an undirected graph. This proof is definitely spoiled by the thing I'm going to do at the end of this lecture. I'm going to write a proof about directed graphs that effectively also proves this. So, try writing that proof yourself. You pause the video right now and try writing that proof yourself. Okay, so we proceed with our traversal, and what I'll observe here is that as of this point in my traversal, with many vertices left to visit, I've already found a path from A to Q, and it was pretty short. It's in fact about as short as I could get. Can I find a path from A to Q in fewer than 2 edges? The answer is pretty clearly no, because if there were a path that was only 1 edge long, that would mean that Q actually is a neighbor of A, which clearly is not the case. So I've actually managed to find, what a weird coincidence. I'm not sure if I want to call it a coincidence. We've managed to find the shortest path, or a shortest path, from A to vertex Q, that vertex that seemed to take forever to reach via DFS. Okay, so we'll proceed with our BFS. There we go. We reached this stage here, and I recall in the previous lecture that when DFS reached this portion of the graph, it wanted to crawl around the outside of it. And I said something like, hey, our next traversal is going to use these two edges. And sure enough, they are now tree edges. Okay, so we'll let this complete. We've now reached the point, you can see where every vertex now has a parent. So we've reached the point where the only vertices left in the queue, all of these yellow vertices, we just have to remove them from the queue and throw them away because there are no unvisited neighbors left to visit for any of them. So we'll just let that complete. There we go, and our traversal is now complete. And behold, our traversal tree. There it is. Notice that this BFS tree isn't as long and stringy as the DFS one. It tends to be wider, it's much wider, and shallower. I think it was maybe this example in the last lecture, maybe another one, where I was trying to talk about how traversal trees are not necessarily binary trees. And I realized that the tree in front of me actually, by a weird coincidence, was a binary tree. Well, here is an example of how traversal trees are not binary trees. You can see that in this tree, the number of children that each vertex has varies wildly. There are some vertices with only one child. There are some vertices with tons of children, so B has 4 children and A has 4 children. There are a couple of vertices with 3 children and one vertex with 2 children. So this is an arbitrary rooted tree. It is rooted because we always assume in traversal trees that the starting vertex can be treated as the root. So here is pseudocode for the version of BFS that maintains a parent array. So I mentioned earlier that, of course, whether we need a parent array depends on the application, but here's a way of doing it. It's nice to use the parent array version, and like with DFS, if you want to economize the number of things you remember, if you're able to produce this traversal, you can do anything you need to do with BFS. Because if you want to do pathfinding, you can use the parent array for pathfinding. If you just want to check which vertices get visited and which vertices don't, you can use the parent array for that as well. So I create a new parent array initialized to invalid, so everything has an invalid parent. I then add my root vertex to the queue, and then I set its parent to be itself. This is the convention I will use to indicate that something is the root if its parent is set to itself. And then as long as the queue is not empty, I grab a vertex, I look at all of its unvisited neighbors, and I detect whether a neighbor is unvisited using the parent array. I just say if it doesn't have a parent yet, well then it must not have been visited already. And then if it is unvisited, I set its parent to be the current vertex V, and I add the new vertex to the queue. I will pause at this point to observe that the running time of this algorithm is the same as the running time of DFS, and I'm not going to make a big deal about that. So basically, by the same logic we used for DFS in the last lecture, we can show, and maybe it's easier to do that with the iterative version, frankly, we can show that the running time of BFS is the same as DFS. It is big theta of number of vertices plus number of edges. Which is great. That's great news because we now have 2 fundamental graph traversals, DFS and BFS. They have the same running time. The only real difference is stack versus queue, although DFS has the benefit that it can be implemented recursively, so you don't need to worry about the stack yourself explicitly. And they do have different strengths and weaknesses. So as I said at the very beginning, it turns out that the strength of BFS, its characteristic, its signature quality, has to do with the shape of this tree. I will spoil it, and what we'll prove at the end of this lecture is that if I look inside a BFS tree, if I start a BFS traversal at a particular starting point, and I produce the tree, and I want to look at paths from the starting point, from vertex A to other vertices, and I use the BFS tree to do that, so perhaps I go from A to H. If I look at the path from the starting vertex via the BFS tree to any vertex that was reached, that is guaranteed to be a path of minimum length in terms of the number of edges. In other words, if we think of a shortest path, and I have to be very careful how I use this term, if we think of a shortest path, in this case, as being a path with the fewest number of edges between 2 vertices, then BFS, if I started at a particular starting point, will find me the shortest path from that starting point to everything I can reach from there. That is the signature property of BFS. It's pretty obvious that DFS doesn't do that. DFS often finds weird, long, circuitous paths. So our 2 traversals have different strengths and weaknesses, and the strength of BFS, probably its signature quality, is finding short paths. I said at the beginning that when you see that, you think, oh, well, in that case, BFS is the best. I love short paths. I don't want to worry about long, circuitous ones. I guess DFS is more of a novelty. Yeah, I can see how you'd make that assumption because we don't yet have a reason to understand why what DFS does can be beneficial, but it turns out it is. It turns out that although DFS generates strange-looking paths, there are other things about its logic that can often be beneficial, and we'll see an example of that, I think, 2 lectures from now. We'll see a case where there is something that DFS does that is really useful that BFS doesn't do. So they both have their strengths and weaknesses, but the strengths of DFS are a little bit more nuanced. They're a little bit more subtle than the strengths of BFS. All right, so what about directed graphs? I think it's similar to DFS in the sense that as long as we respect edge directions, it's pretty clear what we have to do, but we should observe that the resulting tree is quite a bit different looking than what we get with DFS. So we'll start at vertex A as before. There we go. I'm not going to bother with the Q or the parent ray here because we know how to construct those things by now, but I will show each step so that if you want to use this for review, you can do so. Okay, so I visit the unvisited neighbors of A. There they all are. So notice how I'm fanning out from A in all directions at once. And again, BFS is a less adventurous. It's a more conservative traversal than DFS. It fans out gradually from a starting point as opposed to charging through the graph into unexplored territory. Okay, so then I pull vertex B out of the Q and visit vertex C. There we go. And then I look at vertex, the next one is vertex H, and I visit T from there. I visit vertex Q from P. From P, I can't, let's see, from vertex S, I can't do anything. Notice how vertex S has no outbound neighbors, so it's a dead end. So I back up. I then visit vertex D, and then I reach vertex R. There we go. That's interesting. So from vertex R, I do expose a back edge. And it looks like, okay, the slide I guess got duplicated there. When vertex R was added to the tree, I expose the edge RH as a back edge. So far, all of the other non-tree edges have been cross edges, but it is valid to see back edges in a directed BFS. You will never see a back edge in an undirected BFS, and that's actually to do with the fact that it turns out in a directed BFS, you'll never see a forward edge. And the reason that you can't have a forward edge is the same reason you can't have a back edge in the undirected BFS. I know that sounds weird. Really, it's more of a naming hazard. It's because the idea of a back edge and forward edge really doesn't make that much sense in undirected graphs because there's no directions to edges. So what does it mean for an edge to go back or forwards? In directed graphs, those have a specific meaning. So we don't really have a better word for it in an undirected graph, so we choose to call them back edges. But if you thought of them as forward edges, then it's impossible to see those things in a directed BFS or in an undirected one. Okay, so there is a back edge in this graph, and that makes sense because this edge points upwards in the tree. There's no way I would have seen this edge until I got all the way down to R. And by the time I got all the way down to R, I probably have already processed the other end of the edge because it points back up in the tree. So the back edge is something that I can expect to see in a directed BFS. Okay, so we'll keep going. And I guess once I finish the traversal, then it's just a matter of eliminating all the vertices that have no remaining unvisited neighbors. So we take them out of the queue. And we're done. There we go. Notice how, although we exposed a back edge, and in some other graph we might have seen more back edges, we never saw a forward edge in this traversal. And the slides sort of ominously are saying that the absence of forward edges is not a coincidence. It's not just because this particular graph didn't have any. It turns out it's because they are impossible. Here's the complete BFS tree. Now, interestingly, this tree does have some stringiness to it, but that's actually because of the graph. So if I look at this angle over here, so BCDG, that looks a lot like the kind of thing I might normally see in a DFS tree, a really deep branch where a bunch of vertices have only one child. But if I go and look at the graph, I notice that if I go A, B, C, D, G, where's G? It's over there. Then there actually is no other way to reach G than via that long sequence, just because of the directions of edges, or at least there is no faster way to reach G. If I want to get to G, I have to follow 1, 2, 3, 4 edges in any event. There are other ways to get to G. I should be careful what I said there. So I can get to G in other ways, but all of them are going to take 4 edges. So if I want to get there, I could go H, I could go to H, then to T, then to R, then to S. That's 4 edges. Alternatively, I could do H, T, R, H, T, F, G. That's also 4 edges. Or I could do H, T, F, E, G, which is actually 5 edges. So although it's weird that there's this long, deep branch, it actually turns out that is still, if I look at the path from A to G, it actually is the shortest possible path, or one of the shortest possible paths I could create. Okay, so I want to prove that that the existence of a forward edge is impossible. And so the way I'm going to prove this is by stating the theorem that if I consider some ancestor of a particular vertex in a BFS tree, then any edge from an ancestor to a descendant must be a tree edge. In other words, if there is an edge from B to G in this graph, that means that G has to be a direct child of B in the BFS tree and that the edge must be a tree edge. It is impossible for there to exist an edge from a particular vertex to one of its descendants unless that edge is a tree edge, which means, of course, that this is equivalent to saying that there cannot exist a forward edge. So the theorem is equivalent to the statement that a directed BFS will never expose forward edges, or that an undirected BFS will never expose either forward or back edges. And so this will actually prove that this will be the proof of that exercise from earlier about undirected BFS traversals. So we're going to prove this for the directed case because talking about edges from an ancestor to a descendant really seems more natural in the context of a directed graph where there is some directionality. However, because in a sense an undirected graph has less information than a directed graph, that is, you can make an undirected graph out of any directed graphs by pretending the directions don't exist, it turns out that if we prove the theorem for the directed case, it will apply for the undirected case as well, and it's very easy to justify that. So the proof is going to be by contradiction. And what I'm going to do is I'm going to say, suppose we have a vertex U that is an ancestor of some vertex W. Now, I'm not drawing this vertically, it's horizontally, but I'm sure, you can turn your head to the side or something if that makes it easier to understand the ancestor-descendant relationship. So U is an ancestor of vertex W in the tree, so this would be the descendant. And suppose that there exists an edge directly from U to W. I've colored it blue because that's the color we typically use for forward edges. So we're saying basically, suppose there exists some forward edge. Now, this is not an edge in the tree because forward edges aren't tree edges. Instead, there is some way to get from U to W in the BFS tree. I don't know how long it takes, so I've drawn this as a dotted line because there could be a whole bunch of vertices in the meantime. There has to be at least one, and the reason for that is because if there's an edge directly from U to W, and U is the parent of W in the BFS tree, well then this has to be the edge from U to W in the BFS tree. If there's some other path from U to W in the BFS tree, it has to make at least one stop along the way. Otherwise, of course, that would mean there are two different edges from U to W, which isn't allowed. Okay, so carrying through that observation, we end up with this. Because UW is not a tree edge, the path from U to W must involve at least one other vertex. So let's let V be the next vertex after U along the path from U to W in the BFS tree. Okay. Now, the vertex, just to be clear here, the vertex W could be a direct child of V. That is, there could be only one stop between U and W. Or there could be some longer path. We don't really care how long it is. So it could either be that the path from U to W makes a whole bunch of different stops, where the first stop is V and the last stop we're going to call Q, or it just makes the one stop at V. So those are the two cases. We should be aware of both of them. In any event, I want to observe that if we consider the relationship between V and W, notice that it has to be the case that W was first added to the Q after V was removed. Because we'll start with the bottom case. Suppose that W is the direct child of V in the BFS tree. Okay, what that means was I removed V from the Q, I looked at its unvisited neighbors, and W was one of them, which means W wasn't in the Q at the time. So that means that I had to obviously have added W to the Q after V was removed because I added W to the Q while I was visiting V, after removing V from the Q. Okay, so there's the bottom case. The top case is just an extension of that because in the top case, I added W somewhere down the line from V. Which means if I consider, the next thing after V, well, obviously, by the logic I just used, that had to be added to the Q after V was removed. And if I consider vertex Q here, okay, so I've called the vertex Q. That's going to be helpful for this conversation. If I consider the vertex Q here, this was added to the Q after V was removed from the Q. In general, everything along this chain had to have been added to the Q after V was removed. Okay, I hope that's a good enough justification. So in either event, W was added to the Q after V was removed. And this is going to be a problem. So as per the BFS algorithm, if we go look at the pseudocode, W must have been added to the queue along with the other neighbors of U, if you think about it. So if I added W to the queue after V, that means that as of the moment that V was added to the queue or V was removed from the queue, W was unvisited. And if I work backwards in that logic, I realize we have a serious problem here because I obviously processed U long before anything else. U was processed before V was added to the queue. And that means that when I processed U, W was unvisited. And we can see here that W is a neighbor of U, which means that I would have added W to the queue at the same time or around the same time that I added V. So there was a moment in which both W and V were in the queue at the same time. That's a contradiction because I just said that we didn't add W to the queue until after V was removed. So we have our contradiction. Just for the sake of making sure everything is in order, let's go backwards and figure out where we made the assumption that led to the contradiction. Okay, suppose some vertex U is an ancestor of vertex W, and suppose there exists an edge UW which is not part of the BFS tree. Okay, so this actually, you could view this as two assumptions. I view it as just one big assumption. If we do view it as two assumptions, I would say the first assumption can't result in a contradiction. Suppose U is an ancestor of W. Well, obviously things can be ancestors of other things. The provocative statement that clearly leads to the contradiction is this one. I supposed that there exists an edge which is not part of the BFS tree that connects an ancestor and a descendant. And we made this assumption, we did some reasoning, and we verified this assumption resulted in a contradiction, which means if this assumption is true, something impossible happens. And the only conclusion we can draw from that is that this assumption is impossible. This can never be true. And so we get our proof. And so we're going to refer back to this theorem. I will remind ourselves of what the theorem is saying. It is saying that I missed that. If U is an ancestor of W, then any edge from U to W must be a tree edge. Or alternatively, there cannot exist a forward edge in a directed BFS. Or in an undirected BFS, there can be neither a forward or a backward edge. All right, so I'll get us back up to speed. So let's go back and take a look at that BFS, at an example of a BFS tree. Here's the BFS tree from earlier. And I've already observed that there's this signature property of BFS, which is that if you take the path from the root of a BFS tree, it has to be from the root. So it's only paths that have one endpoint at the root that have this property. If I take a path from the root of my BFS tree to any other node in the tree, let's do A to T, and it has length 2 here. The path I come up with will have the minimum possible length of such a path in terms of number of edges. And that is a signature characteristic of BFS trees. And so due to the trees being wider and shallower, of course, the paths found by BFS tend to be shorter. And again, this is not a coincidence. And I have to, remind us of some notation we learned a few lectures ago here. It's been a while. Recall that I've defined the distance between two nodes, which I denote by d of uv, to be the minimum number of edges in any path between those two things. So, of course, there could be lots of paths between two vertices u and v. So if I want to talk about the minimum length of a path, there could actually be more than one of those paths. A simple example of that would be this graph here. So here's a vertex A, and down here I've got a vertex B. The minimum length of a path from A to B is length 2, but there are two different minimum length paths. What I'm arguing here is that, or what I'm going to argue in a minute, is that if I look at the path found through a BFS traversal rooted at a particular vertex U, any path in the tree, so a UV path, will have length which is equal to the distance of UV. It will be a minimum length path. There could be more than one minimum length path. They all have the same length, of course, but it will always find one of them. For any two vertices that are reachable from each other, if I start a BFS traversal at a vertex U, the paths through the tree from U to anything else are of minimum length. They are the shortest possible paths. Okay, so I mentioned that I don't like saying shortest path. And this is going to become quite a thing, because even later, when we talk about algorithms that other people call shortest path algorithms, I will still refuse to call them shortest paths. So the term minimum length path is correct. I mean, that is, if we define the length of a path to be the number of edges, then a path with the minimum number of edges is a minimum length path. I don't want to say shortest path, though, because there are other applications that talk about something that is referred to as a shortest path that doesn't necessarily mean the same thing. Later in the course, we're going to spend quite a bit of time on a particular problem that some people call the shortest path problem. in which case, where some inputs will actually result in paths with lots and lots of edges being considered shortest paths, even if a path with fewer edges exists, because how shortest path is defined can be rather subtle or nuanced in certain cases. So let's be careful about that. So if anybody ever talks to you about algorithms for shortest paths, make sure you ask them to explain exactly what they mean, because the term can mean a variety of different things depending on the context. I want to prove this property. So I want to prove that in the BFS tree rooted at vertex A, the path in the tree from A to any other vertex has the fewest number of edges possible. It is a minimum length path. I want to prove this for a few reasons, one of which is it is a really important thing. It is something we use repeatedly in this course. We really need that for a lot of things we use later in the course. Another reason I want to prove it is I was actually really frustrated making these slides that I couldn't find a complete proof of it anywhere, pretty much, which was really weird. And so in previous cases where I've taught this course, so teaching DFS and BFS, I've never actually presented this proof in full. Instead, I've said this can be proven, and I've said, go look at a book or something, because you can't write proofs of everything. And this time around, I figured, okay, it actually is a pretty important topic. I should include a proof of it. So I went looking for inspiration and discovered that if you go look at most books about algorithms or graph algorithms, they will state this property. They will say that if I perform a BFS traversal, the paths in the BFS tree from the root to other vertices are of minimum length, and then they won't give a proof. They might say the proof is an exercise, which frankly I do all the time, so that's a valid thing to do, but what a weird coincidence that every single book I checked makes the proof an exercise, or it states it as if it's something obvious. It's like, you could easily show this in the margin of this book, so don't bother. I don't know if I like that logic. That's gotten people into trouble before. So I'm going to write a proof of this. I think it's useful to see this proof. It is true that the proof is a little bit mechanical. That is, I understand why a textbook author wouldn't want to include the full proof, because although it's an important proof, it's good to have a proof. Some aspects of it are sort of tedious, but I think for the sake of completeness, somebody has to put this thing in writing. I'm going to prove it using two different theorems. So I've got theorem A and theorem B. Theorem B is the actual result. I need theorem A because when I was writing the proof for theorem B, I noticed that it was getting unreasonably long. It was sort of unwieldy, so I figured I'll split off part of it to make a separate theorem. And that means that we can separate out some of the logic so it's less confusing. Okay, theorem A. If I perform a BFS traversal starting at vertex V0, let's suppose that vertices are added to the queue in this order. Now, I should be very clear what I mean by this. So let's consider this ordering: V0, V1, V2, V3, and so on, up to Vn. What I'm saying here is that vertex V0 was added to the queue before vertex V1 was, and that was added before vertex V2, and that was added before vertex V3. I am not saying that all of these things were ever in the queue at once. I'm just saying that if I number them based on when they were added to the queue, because we know every vertex gets added to the queue at most once during a traversal, if I number them based on that, I should get this numbering. So maybe by the time V3 was added to the queue, V1 had already been removed. That's fine, but V3 was added afterwards, so we number it afterwards. So suppose I number the vertices in the order in which they are added to the queue. In that case, if I consider the depth of each vertex in the BFS tree, then the sequence of depths is monotonically increasing over time. In other words, vertex V0 will actually have to be the root, so its depth in the BFS tree will be 0. And logically, that sort of means that vertex V1 has to have depth 1. For all I know, though, vertex V2 could have depth 1 or it could have depth 2, depending on whether V2 was a neighbor of V0 or not. And vertex V3 might have depth 2 and it might have depth 3. What this theorem is saying is that it's impossible to have a situation like this. You can't have a vertex with depth 1 appear in this sequence after a vertex of depth 2. Depths have to either stay the same or increase as you go from left to right. That's what this theorem is saying. So if I look at the depth of some vi minus 1, that is less than or equal to than the depth of the next vertex vi. And of course, this observation generalizes. So what this is really saying is that, moreover, the depth of, let's say, vj is less than or equal to the depth of vk in any case where j is less than k, basically. So if I notice that that goes in both directions, actually. So if I notice that the depth is less than or equal, then I can say that means that that vertex vj had to have a lower number. So j is less than k in that case. Okay, so that's the point of theorem A. I'm going to prove that by induction on I. So notice how the theorem was stated in terms of some index I. I'm going to use induction on I, so I can be 1 here, because that means the depth of V0 is less than or equal to the depth of V1. I can be 2. I can be any value up to n. I'm actually going to do induction on this value I, and it's sort of a weird use of induction, although it's valid, because unlike a lot of our previous uses of induction, which prove something about an infinite number of values, that is every value of I from some starting point all the way to infinity, this is actually doing induction over a finite number of values, or at least finite in a specific case. I mean, obviously n can be as large as we want in general, but for a specific graph, n is a finite number. Doesn't matter, I can still do induction. Okay, so my base case is relatively simple because I can consider I equals 1. Vertex V0 is the very first thing that was ever added to the queue, which means it has to be the root, because that's the way BFS works. Okay, so what about vertex V1? Well, the only time I would have added vertex V1 is when I was processing vertex V0. That's the way BFS works, which means that the depth of V0 is 0, because it's the root, and the depth of V1 has to be 1, because it's a child of the root. Okay, so the depth of V0 is less than the depth of V1, and the theorem holds. We're good. Now, the hypothesis is simply that the theorem holds. It's a stronger hypothesis. Suppose it holds for every pair of vertices up to Vi, basically. So it has to be stated in a weird way because it's a stronger hypothesis. Suppose that the depth of Vj minus 1 is less than or equal to the depth of Vj for all j up to some value I greater than or equal to 1. In other words, suppose that the theorem holds for this part of the sequence. And then my induction step will be taking a look at this vertex and showing that the theorem has to hold there as well. Okay, so the induction step is consider I plus 1. So we'll consider Vi plus 1 in my sequence. Now, we're deep into the BFS tree by now. We're certainly no longer at the root, because we know the root is over here, and we specifically defined I to be greater than or equal to 1, which means I plus 1 is greater than or equal to 2. So we're not dealing with the root, which means it's logical to say that both Vi and Vi plus 1 have a parent in the tree. So neither of them is the root, so they must both have parents. Let's let Vp and Vq be the parent of Vi and I plus 1, respectively. So one thing to note here is that remember that P and Q are numbers. What I'm actually going to be reasoning about in this proof is where these two things fall in this numbered sequence. And I'm going to be using that to establish my result. Right now, I've drawn VP and VQ at sort of indeterminate positions. What I really want to reason about, though, is that I want to show that VP and VQ have to be in a certain order in the sequence. One has to come before the other. So right now, I just have them both sort of tied. You know, if we look at the left to right order, I don't really know which one comes first. So I've written them both tied in my little sketch of this proof. I should, of course, as usual, add that the sketch is just for the sake of me drawing nice pictures. The actual proof is what I've written in the text. Okay, so one special case to get out of the way before anything else. Suppose that P equals Q. That is, VP and VQ are the same thing. Well, in that case, that means that Vi plus 1 has the same parent as Vi in the tree. The parents are the same thing. In which case, of course, because they have the same parent, they both have the same depth, because they're both children of the same thing. And if their depth is the same, then the theorem holds. Okay, so we're good. Otherwise, if P is not equal to Q, well, let's consider what happens in that case. So in that case, obviously we can observe that because of the way we define this numbering, Vi plus 1 was added to the Q after Vi, because the numbering is based on when things were added to the Q. That means that if Vi got added first, then the children of VP, the neighbors, the unvisited neighbors of VP, had to have been added to the Q before the unvisited neighbors of VQ. Okay, and so what that tells us is that means that P has to be less than Q. VP has to have been processed first. So VP was removed from the Q first, which means it was added to the Q first. So if P is not equal to Q, we can conclude that that requires that P is less than Q. Because if P were greater than Q, we'd have a problem. How did Vi get into the Q so quickly if we hadn't processed its parent yet? So because we processed its parent before we processed the parent of Vi plus 1, the parent had to have been processed before the parent of, I think that what I just said was a tautology. I guess that means we can move on from this slide. Okay, so since P is less than Q, so since they fall into the ordering like this, then we can apply the induction hypothesis, because we know that, of course, Vi plus 1, that there's no way that the parent of Vi plus 1 is equal to Vi plus 1. So the parent of Vi plus 1 is at most Vi or earlier in the sequence, which means the hypothesis applies. And because I stated the hypothesis strongly, it doesn't matter exactly where P and Q are in the sequence. We know that as long as P comes before Q, so P is less than Q, then we can apply the hypothesis. So by the hypothesis, the depth of VP is less than or equal to the depth of VQ. And so if we now think about the depth of VI and the depth of VI plus 1, okay, well the depth of VI is just equal to the depth of its parent plus 1. That's how a tree works. And so the depth of VI, which is the depth of VP plus 1, is less than or equal to the depth of VQ plus 1, because the depth of VP is less than or equal to the depth of VQ. And so we've now shown that the depth of VI is less than or equal to the depth of VI plus 1. And that's what we wanted to show. And therefore the theorem holds for the case for I plus 1, for VI plus 1, and therefore by induction, the theorem holds for all I greater than or equal to 1. And there's theorem A. Now, theorem B is the actual result we want to prove. So again, let's number the vertices as we add them to the queue during our BFS traversal. So the number of vertex gets corresponds to the order in which it was first added to the queue. There's no requirement that any particular pair of vertices was ever in the queue at the same time. We're just numbering them based on when they were first added. And then the statement of the theorem is, if the depth of each vertex is denoted by this term, as we have done so before, then it is the case that the depth of each vertex in the tree is the minimum distance, or is the distance, which is the minimum length of a path from the root to that vertex. In other words, if I follow edges in the tree from V0, the root, down to whatever vertex I want, Vi, the path I take will be the minimum length path, or in quotes, a shortest path from the root to that vertex. And this is the proof of the signature property of BFS, a proof that I have had basically no luck finding anywhere else in any other books, any of the sources that I've consulted. Okay, the proof is by contradiction. And what I'm going to do basically is find a way of using theorem A to prove this result, to prove theorem B. Okay, so by contradiction, suppose that there exist vertices in some graph. Suppose you do a BFS traversal of a graph, and in this graph there's one or more vertices such that the depth of those vertices is not equal to the distance of those vertices from the root. I have to be very careful how I phrase this, because there could be more than one of these vertices, and if there are more than one of them, I have to be very careful which one I choose. So let's now say, suppose there are some of these vertices, there could be one, there could be a million of them in the tree, and I want to show this is a contradiction. What I'm going to do is talk about a specific one. So suppose these vertices exist, and choose Vi to be one of them with this property. I want one with the minimum real distance. So the distance is the length of a minimum path. Choose Vi from all the vertices where this is the case. Choose Vi to be the one whose real true distance, the length of a true minimum path, is as small as possible. The trick that I'm going to do later is I'm going to come to a point where there has to be either the theorem holds, or there has to be a situation where there's some vertex with an even smaller value of D that this also applies to, which will be a contradiction because I chose Vi to be the one that has the smallest possible value of D. Okay. So I choose Vi to be a vertex with the smallest possible distance from the root, true distance, that has this situation, that where the depth is not equal to the true distance. Now, we know that because we did a BFS traversal and we have a BFS tree, even if the depth of Vi, so let's say Vi is all the way down here, even if the depth of Vi isn't equal to the minimum distance, the actual distance from V0 to Vi, we know that there is a path from V0 to Vi because we have a path in the BFS tree. And so, of course, it has to be the case that the true distance, the minimum length of a path, has to be less than the actual depth in the tree. Because we just said earlier that the depth and the distance are not equal, so they can't be less than or equal to each other. So, obviously, the depth is greater than the minimum distance. That's the way the minimum distances are defined. Okay, and then finally, let's let Vj be the parent of Vi in the BFS tree. So what does that give us? It gives us this situation. Here's V0, and then here's Vi, and then in the BFS tree, there's some path from V0 to Vi, and the second to last vertex is the parent Vj. Okay, and obviously, because of the way trees work, the depth of Vi is the depth of Vj all plus 1. Now, we said earlier that the depth of Vi is not equal to the true distance. So there is a shortest path, a path with the minimum number of edges that is shorter than the path in the BFS tree. Okay, so there must exist, because the true distance is less than the depth, there must exist some path P of length less than depth Vi. That is, it should actually be of this length, but all we care about is there's some path of length less than depth vi. Now, let's choose vk to be the second to last vertex along that path. So if I follow a path from v0 to vi in the BFS tree, the second to last vertex is the parent in the BFS tree, vj. There is some shorter path out there, and the second to last vertex in that path we're going to call vk. So based only on that, what do we already know? Well, we know that there apparently is a path shorter than that in the BFS tree. That's what we're going to show is a contradiction in a minute. And we also know that because of the way distances work, think about the distance, the true distance, the minimum distance from v0 to vk. Obviously, it makes sense that the path from v0 to vk along this path to vi should be a shortest path. I'm going to redraw this a bit. There we go. The distance between v0 to vk should be the length of that path, the path from v0 to vk along the way to vi. Because if there were a faster way to get to vk, then there would be an even faster way to get to vi. So if I consider a true shortest path p from v0 to vi, the portion of it that goes to vk should be a shortest path from v0 to vk. Okay, what is that all telling us? What it's telling us is that the distance from v0 to vi has to equal the distance from v0 to vk all plus 1, because there can't exist a shorter path from v0 to vk unless there would be a shorter path from v0 to vi. All right. Now, obviously, the distance from v0 to vk is shorter than the distance from v0 to vi, because I get to vk on the way to vi. Now, what this is actually telling us, based on that strange assumption I made earlier, so remember that I made a big deal about this phrase here. Vi was chosen to be the vertex with the smallest distance that has this problem. So there could be vertices out there with smaller distances, but none of them are allowed to have this problem. All of them, any vertex with a smaller distance than the distance to vi must have the depth equal the distance, because vi is the one with the smallest distance that has the depth and distance not equal. Okay, so because of the observation that the distance from v0 to vk is less than the distance from v0 to vi, then that means that the depth of vk in the BFS tree has to be the distance, because otherwise we already have the contradiction that we're looking for, because we chose vi to have the minimum possible distance among vertices which have this problem. Okay, so what does that tell us? That tells us that if I look at the path from v0 to vk in the BFS tree, it is a shortest path. And so therefore, the depth of vk has to be less than the depth of vj. Why do we know that? Well, we know that the length of this path here is longer than the length of this path here. We also know that the distance, and therefore that the distance from v0 to vk has to be less than the distance from v0 to vj. And if the depth of vk is equal to the distance, and the depth of vj is equal to the distance, well, that means that the depth of vk has to be less than the depth of vj. Suppose the slides are pointing out, suppose that if the depth of vk were equal to the depth of vj, then we'd end up with something that doesn't make any sense. We'd have the depth of vi is going to be equal to the depth of vj plus 1, which is the depth of vk plus 1, which is the distance to vk plus 1, which is the true minimum distance. And that doesn't make sense because we assumed earlier that the depth and the distance were not equal to each other. So of course that couldn't happen. Therefore, it must be the case that the depth of vk is less than the depth of vj. And now we can bring in theorem A. So because the depth of vk is less than the depth of vj, by theorem A, if we think of our numbering, so the numbering of vertices in the order they were added to the queue, theorem A tells us that k has to be less than j. In other words, in that ordering, vk appears first. It appears before vj. This is a contradiction, though, because what that's telling us is if vk was added to the queue before vj, that means that the neighbors of vk were processed before the neighbors of vj. And if that was the case, then we would have brought in vi as a child of vk, not as a child of vj, and that's a contradiction. We already proved that vj and vk aren't the same vertex, and we just said that vj is the parent of vi. And then we proved by other means that vk has to be the parent of vi. These can't both be true. That's a contradiction. And again, just to keep everything clear, let's go back and figure out where we made assumptions. So we did a bunch of reasoning, but if we trace back to the place where we made an assumption, it's going to be quite a ways back. It was here. Suppose that there exist vertices where this holds, and let vi be one of those vertices. The only assumption was that there are vertices where this problem can occur. And because we showed that if that is the case, a contradiction ensues, we now know that this is impossible. And therefore, in a BFS tree, we have that the depth of a particular vertex in the tree is equal to the length of the minimum length of a path from the root of the tree to that vertex. And therefore, that the paths you get in a BFS tree rooted at v0 are the shortest possible paths in terms of number of edges. And so we've now finished our proof of theorem B, the characteristic property of BFS, which is that BFS trees contain minimum length paths from the root to other vertices. And so therefore, yes, okay, I missed this slide. So no vertex with a mismatch of depth and distance exists, and the theorem holds for all vertices. So what have we learned about DFS and BFS? Well, both of them are fundamental graph traversals, and if I start them off at some starting point, like this vertex A, I will visit all of the vertices reachable from A, and I will form a traversal tree that describes the paths that I follow to get to all of those vertices. Now, the shape of the traversal tree can vary. DFS produces those characteristic stringy trees resulting from its much more adventurous, aggressive traversal. So as you can see, it just charges right into the graph, and as a result, it ends up reaching certain destinations via a very strange circuitous route. Whereas BFS is this more conservative, even-handed traversal, I guess, that spreads out very evenly from the starting point. And we just proved that not only does that result in a tree that's a bit more wide and shallow, but in fact, the paths that we produce in that tree are as short as possible. We can't do any better than that. So if I want to find a quick routing from A to, let's say, vertex Q here, a routing that uses as few edges as possible, and in some cases, using fewer edges is good, although we'll see later in the course that there are plenty of cases where, depending on how you're modeling your problem, you don't mind using a lot of edges, you care about some other quantity instead in terms of what a shortest path is. But if we care about covering as few edges as possible, if I use BFS and generate the BFS tree, the path from A to Q in that BFS tree is as short as it possibly could be. There could be other paths of the same length, other paths of length 3, but there will never be a path of length 2. BFS finds the shortest path in terms of the number of edges on it. Both of the two fundamental traversals have the same running time, which is the number of vertices plus the number of edges. I didn't go through that in much detail today, but it's by pretty much the same reasoning as we used last time for DFS. BFS has an advantage in any event where the short path or a shallow tree is beneficial. And it's true that I keep claiming DFS has some secret advantage, but DFS trees look sort of chaotic, again, because DFS just charges right into unexplored territory. It does turn out that the recursive structure of DFS trees, in particular the fact that when I finally leave a vertex, when I finally unwind from recursion or pop a vertex off the stack, I can make certain assumptions about which other vertices must already have been visited in all cases. That does lead to DFS having certain advantages. It's just not obvious. It's sort of behind the scenes. We're going to see it, I think 2 lectures from now, we're going to see a case show up where we can exploit that property of DFS to great effect, something we can't really do with BFS. And on the other hand, it is true, though, that there are a lot of applications of traversals that don't care at all about the structure of the tree. The running time of both traversals is the same. And if I'm asking very simple questions like, could you find me all of the vertices in the connected component of A? Or, is this graph connected? Well, both DFS and BFS can answer that question very efficiently. So if I want to know whether a graph is connected, I just start at a particular vertex, run whatever traversal I want, and if it visits all vertices, then the answer is yes, the graph is connected. And if it doesn't visit all vertices, the answer is no, the graph is not connected. And as we saw, if I run a traversal starting at a particular starting point in a disconnected graph, the vertices I visit are the contents of the connected component containing the starting point. So in those applications and many others, it doesn't actually matter that much exactly what paths you find or what tree you come up with. All it matters is that you visit every vertex that's reachable from the starting point. And in those applications, it's pretty much up to you. So I've mentioned before that I sort of have an affinity for DFS, and that means that often when I want to just test reachability or test connectivity, I'll just write DFS. But in the same case, you might write BFS, and that's fine. Unless you care about the characteristic properties of DFS or BFS, there are tons of applications where it makes no difference, and therefore it's pretty much up to the implementer which one to use. One thing that's been missing from the last couple of lectures, and actually all of our graph lectures so far, we haven't spent that much time talking about ways of modeling actual problems, so beyond graph theoretic things or here's a graph, let's do a traversal, actual problems that do some actual applied task with graphs and graph traversals. Now, that was an unpleasant omission, I guess, because it's nice to have applications, but I wanted to wait until we had lots of knowledge. Until we knew about the terminology of graphs, but also had some basic graph algorithms to play with before I talk too much about those applications so that we can actually solve the problem once we get applications we can model with graphs. I'm going to talk a bit about that in the next lecture, and then we're going to proceed after that lecture to talking about some more advanced graph algorithms that build on these basic traversals.